SPAC presentation by Todd Gamblin at not the opposing lab, Lawrence Livermore National Lab. And Todd's going to give us an overview of a package manager for HPC called SPAC. And this project's been actually in operation for quite some time at the labs, but I'm not sure how far out it's broken into the academic space. So I'm really interested to look into this and see where this project is in its current state. So Marissa, if you would go ahead and hit record.
Done.
And we will hand it over to Todd and let him get started.
Okay, great. Can people hear me okay?
Sounds good.
Yep. Okay, great. Okay, so I'm going to talk about SPAC. It's a package manager that I created, I guess, 5 years ago now for HPC. And it was meant to reduce software complexity. Basically, this started as a sort of anger project because I was sick of building things for supercomputers. So if you, let's see if I can get the arrows to work. Yeah, so if you look at what modern HPC software looks like, here's an example of a package that you might want to install. This is Nalu from, I think, NREL. It uses Trilinos. It has a whole bunch of other dependencies. And basically, this little package over here, this is Nalu. And this is all the other stuff that you need on your system to make Nalu work. And so you can see that it's a lot of stuff. That's a fairly minor package. So, I mean, if you look at bigger things like DL2, which uses a whole lot of solver libraries, it can get even more complicated. And if you bring in, say, the R software ecosystem, things can get even nastier, where like this is R minor. All the stuff over here on the left is R. R is kind of in the middle. A few of the R packages have native dependencies over here onto the into the sort of system library side. And there's a whole lot of stuff that's needed over there as well. This can get really nasty, and I mean, even our proprietary codes at Livermore have a whole lot of dependencies. So if you look at, say, one of our production multiphysics codes here, Aries basically has all this blue stuff is open source. It's external open source that we rely on, that we have to keep up with, that we basically have to make sure that our software continues to work with. And all the other things like the red, the green, and the yellow, those are Livermore built libraries. Some of them are open source, but even they have pretty complicated connections in there. And everything in there needs to be HPC to get the best performance, and that can be a pretty complicated task. So if you look at the whole exascale computing project, so I don't know if people are familiar with this. This is a large project in DOE. It includes Livermore, Los Alamos, Sandia, so the NNSA labs, plus Argonne, Oak Ridge, and Berkeley Lab. There's actually 17 labs participating in ECP, but those are the 6 core ones, and those are the ones with the big HPC centers. ECP is tasked with creating the software stack for future exascale systems. And if you look at everything there that we're supposed to deploy, there's something like 15 applications. I think it's actually more like 25 now. 80 or more software packages in the stack, different target architectures that we care about, lots of compilers, 10-ish programming models if you count all of these. So OpenMPI, the different MPI implementations, OpenMP, CUDA, and also emerging things like Raja and Cocos for performance portability. And then multiple versions of each of those. If you multiply that all out, that's like 1.2 million combinations of software that you could potentially build. And this can get to be unwieldy if you have to build it for every system that you get on by hand. So what we really want to do is make a way to sample that space and to install different combinations of those packages on demand. Because every application is going to need something slightly different, or at least that's what we're anticipating. Developers and users and facilities typically have to dedicate lots of FTEs to building and porting this stuff, and it takes a lot of hours to make sure all of these things are installed on a system. And typically you try to install these things and you end up trading reuse and usability for performance. So you end up building like a lowest common denominator binary that's not optimized for the system because that's what you could get to work, and maybe it doesn't perform as well. So what we're trying to do with SPAC is to make it easier to rely on other people's software and to keep it performant, to make sure that you can expand this whole space if you want to. You can build the combination that you need and you can get the performance you want, but you don't have to know how to build everything. So just as sort of a flashback to when I started, this was how you could install software on a Mac in around 2013. You would say port install libelf, or now you'd say brew or something like that. You would use a package manager. It would try to build that thing, and then you would have that thing. You would basically refer to it by name. If you tried to install one of these things I showed for your HPC system, it might look more like this, where you download all the 16 tarballs that you need, you start building, and then you go and you run make, and you fight with the compiler, you run make again, you tweak the configuration arguments, you configure, you make install, you fight with CMake, and then finally you get something, you run it, and it seg faults, and then you start that whole process over. So this is basically what I was irritated about. Most supercomputing sites have modules, and I get this question a lot when I try to present SPAC. People say, well, what about modules? I mean, there's all sorts of software available in modules. Why do I need to install new things? And what I think people don't realize, and what maybe this community would empathize with, is that there are actually a lot of people behind the modules making sure that the installations work. And so, modules are not magical. They don't actually install the software. They just let the users get it into their environment easily. And so SPAC is not a module system. It's an installer and a package manager. So and it will generate modules, but it's doing a lot more than what the module system does. Containers is another thing that frequently comes up, and I think containers provide a great way to reproduce and distribute a software stack that you've already built. But someone still needs to build the container. It's a similar thing. And that's not trivial, and actually in HPC, the containers are starting to look more and more machine specific. So if you build a container that needs to use the GPU, you need some way to go and talk to the system hardware or the driver from your container. And so there ends up being a machine specific part in there. Similarly with MPI, you end up having to either use an MPI that matches the host MPI on the system, or you may have to sacrifice some performance and maybe not use the fast network from within your container. So I don't think containers are a panacea. You still need a way to build the containers that you want on demand. And I think in HPC particularly, because the hardware is so diverse and you actually need to use fancy networks and GPUs, you're going to find yourself having to build containers for specific machines. And so maybe you have to deal with a few more of them than you would in the cloud, where you can sort of assume a common Linux environment. So SPAC is the package manager that we made to try to address these problems. The idea is that you can go to github.com/SPAC/SPAC. So go visit that and check it out. You can also go to spack.io for sort of an overview, and we're on Twitter. You can clone the repo and just get going from there. You can optionally source this setup.env.sh file. And then to install a package, you just say SPAC install package name. So kind of like what I showed for the Mac installation a few slides ago. When you do this, SPAC goes and fetches HDF5. It fetches all the dependencies for HDF5 and basically their source from the internet. It puts them in a known location that you don't have to think about, and it goes and builds them in a staging area and installs them into the SPAC directory. And unlike typical package managers, SPAC allows you to customize a lot of different variants of the same build. So if you don't just want the default, you can customize the compilers that you use for these things, you can customize the MPI implementations and other dependencies, and you can customize build options. And I'll show a little bit about how that works. So on the command line, like I showed before, if you just say SPAC install package, MPI leaks is a tool that we developed here at Livermore for managing or for finding handle leaks in MPI programs. So if you allocate a request object and then don't free it, MPI leaks will find that. If you just want that tool, you can say SPAC install MPI leaks and get a default configuration. If you want to customize what version it is, you can say SPAC install MPI leaks at version 3.3, and it'll go download the tarball for that and build it instead. If you want a particular compiler, you can say %gcc at a particular version as well. And you can have build options exposed by the package authors, and you can actually inject flags into the build if you want to. You can cross-compile on platforms like Cray. I'll talk a little bit about how we're working on specific targets for just basic Intel chips and ARM, where you could have specific architectures. I'll talk about that later. And then finally, this whole syntax is recursive. So if you want to apply any of these types of constraints to dependencies of the package, so if you have MPI leaks and you know that it uses MPI, you can say, yeah, build with this version of MPI, build with MPITS 3.2 instead of some other version of MPI if you want to. So that lets you customize a lot of different things about the build straight from the command line. There are also configuration files you can use to set this up, so if you want to fix things for, say, your entire stack that you're building on your machine. On the command line, if you want to list what's available, you can just say SPAC list, and it will print out the full list of packages that are in SPAC. There are over 3,000 built-in package recipes, and then if you want to build private ones yourself, or if someone has built them and you want to use theirs, you can actually have private repos as well. And then I guess the important thing to note here is that when you say list, you're actually showing the names of available packages, but none of these is actually an installation. These are the recipes that are available. You can think of them as sort of templates for packages. And if you type Spack find, it's going to show you what's actually installed. And so if you just clone this, you'll see nothing here. But if you run it from the command line with some things installed, you'll see something like this. And so what this is showing is the actual installations of different packages. And so the difference here is that it's not just a name, it's not just a recipe, it's the recipe plus the version that's actually installed. And the sort of unique thing about Spack is that all these different versions can coexist on the system, which that'll be familiar to HPC people who frequently install lots of different versions of packages. But one difference about how we link things to maybe how most sites link their packages is that we use RPaths pretty pervasively. So we install these things so that they know where to find their dependencies. And the rationale for that is basically that if you knew what you were doing when you built the package, or at least the package manager did, and you shouldn't have to load the package plus all of its dependency modules in order to run it, because by the time you get around to running it, you probably have forgotten all of those details. The other thing that this does is for each of these packages that it installs is it does generate module files. But like I said, the binaries are built so that they actually know where their dependencies are using RPaths. And so you don't have to use modules if you don't want to. If your user finds an executable in a directory and just runs it, it should just work.
Hey, Todd, we've got a quick question.
Okay.
Does Spack build RPMs, is in the chat box?
It does not build RPMs, but I will talk about how it can do binary packaging later. So it's not it's not an RPM format, but it will build its own relocatable binary packages. Thanks. And they can be signed as well.
Okay.
So the other thing that you can do here is you can sort of dig down into all the provenance for these things that you've installed. So if you want to see, for example, there's multiple versions of some packages here. So you can see there's 2 versions of Dynance that look about the same in this view, and 2 versions of adept utils over here. You can find a call path here under GCC 447, and there's another call path library down here under Intel 1501. And so if you say Spack find call path, you'll just see the 2 packages that match that. And so and I guess these are the 2 compilers that it picked up. And if you dig down really deep in there, you can see that you can see why these things are different. So in addition to this one being built with Clang and this one being built with GCC, if you run Spack find-d and L to show the hashes, and I'll talk about that in a little bit, you can actually see that these things were built with different versions of Boost. So this one over here was built with Boost 159, and this one was built with Boost 155. So you get a lot more detail about the detailed provenance of all the dependencies that are installed. The packages themselves are templates, like I said. So in Spack, per package, there's one of these files. If you have a package like Dynance, there's one file called Dynance, or in Dynance/package.py in the package repo. And what it is it's just a Python class. So every class in some way or another extends package. We have some specialized packages that are made for particular build systems, and those are sort of described in the docs. They just make it easier to build with common conventions for things like CMake and AutoTools and some other build systems. And then within the package, there's some metadata that says, here's a comment describing the thing. This is the homepage for the package. This is the URL that tells you where you can download it. There are version directives, and so these say that these are the available versions of the package, and these are checksums that you can use to verify the file once it's downloaded. Spack is smart enough for some URLs to automatically infer from this top-level URL what the particular version URL should be. So if you wrote, a path to something that has versions in it like this, Spack could extrapolate and say, oh, okay, well, 821 must be available at a similar location. For packages that have crazy locations for URLs or ones that are not regular, you can just put a URL per version if you need to. So if you need to override that because Spack isn't figuring it out right, you can actually just say per version which place to download the package. These are dependencies, and so basically this says to build Dynance, you need CMake installed, and it's going to link against libelf, libdwarf, and Boost. And you can see in here that this is using the same syntax as the constraints that I showed earlier. So if you depend on boost, you don't just have to depend on boost. You can actually say, well, I require boost 1.42 or higher, and I require it with this multi-threaded option. So if you depend on a specific feature, you can that's actually integrated into the dependency model, and Spack will just build you a boost that satisfies that requirement. And then the install method down here is designed to look pretty much like shellcode. So some of this is a Pythonism. So like with this working directory, and we're going to create it when we build it, go and run cmake with these arguments and make and then make install. And the other thing here is that you are past the spec of all of your dependencies in your own package. And so like I said, these are templated. So essentially, when Spack constructs a dependency graph for the thing that you're going to build, it passes that in via this spec variable. And you can query that and say, okay, I need to depend on boost. Where's that installed? And so you can say spec sub boost.prefix.include, spec sub boost.prefix.lib to get the include and library directories that you need to pass here to the build line for Dynast. And so the idea here is that you don't spend a lot of time checking what's on the system. Spack just tells you where your dependencies live, and they can be external packages. There's a way to configure that. And then you translate this spec description into build instructions in your package.
So it looks like that covers one of the two questions. Todd, Karen Tomko asked about the external dependencies with the package not installed via Spack, and I think you just touched that.
Yeah.
Feng Lu at Georgia Tech says, how user can distinguish the model files with the same name from different compilers?
Oh, the module files? So
yes.
So so within Spack, if you just query the installations, you can see stuff here where we're differentiating by compilers. So we have the metadata. When you generate the module files, you can definitely include the compiler name in the module name if you want to. So but by default, I would say Spack has a fairly bare bones module file configuration because the sites tend to customize it for themselves. But I mean, it does support both Tickle modules and LMod. And so I guess in LMod, you wouldn't actually have different module names per compiler. You'd load the compiler first and then load the module for the package. And it would remember what compiler you picked. For Tickle modules, there's templates that you can put in your configuration to say how the module file names should look. And so that's in the docs if you want to go look into that. I don't want to get too far into the details here.
Okay, right. Got it.
There's probably the best place to look for that is the module tutorial. So if you go to the spack.readthedocs.io site, there's a tutorial there, and there's a section on modules that goes through how to configure this stuff. Okay, so I talked a little bit about Spack's installation model, and this is what it looks like. If you install a package like MPI-Leaks, if you can think of it as a directed acyclic graph or a DAG. And basically, MPI-Leaks depends on call path and MPI. It needs to make calls into those libraries. And then call path depends on Dynast and MPI and so on. And so the way that actually gets installed on the disk is that Spack takes this entire DAG with the metadata that's associated with it. So in order to distinguish the installations for different versions of packages, we basically imagine that this node had the MPI-Leaks, the version, the compiler version, all the build options, flags, and things like that on it. We take that entire description for the DAG and we generate a hash. And then the directory layout looks something like this, where under opt in the Spack directory, there are per architecture directories, per compiler directories, and then there are per package directories. And each one is suffixed with this hash. Really, all this, the prefix stuff here, it's just metadata so that you can actually browse the install directory and you can see about what's installed there. The suffix here is really all you need to make this unique. It's a SHA-1 of this whole DAG configuration. And so, like I said, when we install something in these directories, if we install MPI-Leaks, it'll have RPaths in the binary out to this call path library. Call path will have RPaths out to Dynast and so on, so that these things know where to find their dependencies in this large directory. So there's no need for users to necessarily use modules or set LD library paths, but like I said, they can use modules to get it in their environment, and that's how they usually do on HPC systems. And so what this gets us is that there's really no limit on the number of versions you can have installed. We've seen sites where people have set up elaborate naming schemes, but then there's always sort of like one-off version that you need of something that doesn't fit in the naming scheme. So you add like .1 or dash special to the directory name, and then it becomes pretty difficult to navigate these directories once you've set that up. And so we're trying to provide a unified interface here in terms of the way that things are installed, and then the way that you can query them and view them. You can use either Spack find, or you can generate whatever module scheme you want to look at these packages. And the modules, if you're not happy with the module scheme initially, you can always go and tweak the configuration and regenerate the modules for all the packages if you want to do it slightly different configuration. The other thing that we do is we let you depend on interfaces and not on specific implementations. So this comes up a lot in HPC for things like MPI or BLAS or LAPAC. Those are not necessarily implementations of a library. They're actually those are interfaces, and there are lots of implementations of those libraries. And so in the package, like MPI leaks, the package actually says I depend on MPI. And so it's like this down here. It might say I depend on MPI at version 2 or higher. And then the MPI provider packages like MPIG, MVAPIG, OpenMPI, they tell SPAC when they provide MPI. And so MVAPIG provides MPI at version 1 up to version 1. When it's at version up to 1.8. And then at MVAPIG 1.9 or higher actually provides the MPI2 interface. And so you can use it for programs that require MPI2. Similarly, OpenMPI, different versions of OpenMPI provide different versions of the MPI spec. And so what this lets you do is that the packages can say, they can express what requirements they have on the MPI implementation. And then a user can actually say, install MPI leaks with a particular MPI version, and SPAC will complain if it's one that doesn't support what the package needs. So the way that this works is, and this is what's really going on when you say install, is we have this process called concretization. And so the syntax is designed so that if you say SPAC install MPI leaks, and then you provide a bunch of constraints like this, that is basically you telling SPAC what your requirements are. And it creates a graph that is sort of partially filled out. You have a few constraints, but you don't have the full thing. The concretization process takes that and turns it into essentially a fully filled out graph. It fills in the blanks, it picks sensible defaults for things, or it picks things according to the requirements of other packages. And that is actually a hard thing to do. It's an NP hard problem to resolve all these constraints between different packages because they can conflict, and you have to do this NP hard search to find versions that satisfy all the constraints in the graph. We're currently using heuristics that work okay for this, and we're working on a new version of the concretizer that would do a full SAT algorithm to work these things out. There are some cases right now where SPAC will find a conflict where none exists. And this is a little more on why that's hard. I don't think I need to get too far into the details here. So we made this tool, I guess, in around 2013. We started using it at Livermore in production in, I guess, 2014. And we wrote a paper for supercomputing in 2015. And since then, it's sort of taken off, and a lot of sites have started using it. SPAC, I guess, when I started writing it, had around 170 software packages when we actually presented the supercomputing paper in 2015. And since then, we've gotten contributions from external people, and we've gotten up to over 3,000 packages. There's over 1,100 monthly active users on the doc site, and we have over 300 contributors total. And this is a plot from Google Analytics showing kind of where everyone's from. And so you can see that SPAC's used in a whole lot of places. It's pretty concentrated here in the US, and then there's this giant dot around Livermore. But then there are lots of other sites using SPAC, both in the US and in Europe. And also, I guess we have some Brazilian users, and we've gotten Chinese and Japanese users, and even Australia as well. So there's a fairly large community around this. We have a lot of activity on the GitHub site. We merge a couple hundred pull requests every month. Most of those are package modifications, small version bumps, and things like that. But people do contribute features as well. And it's not just me, although this is showing a month where I contributed a lot of stuff. There's actually, it's a pretty balanced community. We get a wide range of contributions from lots of different people. We've done tutorials at supercomputing for the past 3 years. And we're going to do another one. We're going to do our first one at ISC this year in Germany. And we're also trying to do one at PIRC this year to reach out into the champions community. This is a graph of the contributions to SPAC over time, just to give you an idea of where these packages are coming from. So this is lines of code over time in packages by organization. And so you can see here, this is sort of me making packages up to 2015 right here. And then we started getting contributions from other folks. And so if we had remained just a Livermore project, we would still be at, slightly more packages than we had in 2015. And we've benefited a whole lot from all these contributions that we've gotten from the external community. Down here, this is contributions to core. So Livermore is still developing a lot of the core. We've gotten some really big contributions from EPFL and from Fermilab. Fermilab actually contributed the binary packaging capability and some of the more advanced features that we've gotten recently, which is pretty cool, them and their collaborators at CERN. So we've benefited a lot from those collaborations. It's being used on a lot of the top HPC systems. So it's used to build the full software stack on Summit. The Oak Ridge folks said that before they started automating their deployments on the big machines with SPAC, it would take them about 2 weeks to build the full set of 1,300 packages that they have to install. And they can do that automatically overnight in around 12 hours now. They have a GitLab instance that basically runs SPAC and deploys things. EPFL is similar. That's in Switzerland. They deploy their whole software stack with Jenkins and SPAC. And other DOE sites are starting to pick up SPAC as well. We've even gotten adoption in China at Shanghai Jiaotong University. ECP is using SPAC as part of their software release process. I'll talk a lot more about that later. And then within the high energy physics community, like I said, the Fermilab and CERN folks have started using SPAC to manage some of their larger, simulation codes that have to do with the Large Hadron Collider. So that's pretty cool that we've actually gotten outside of the sort of mainstream HPC community there. We released SPAC 012 back in November, and this was actually, we were originally under the LGPL license, but we switched to be more permissive to Apache 2 or MIT. We had some places saying that they had to ask permission to use SPAC under LGPL, whereas if we were to use a permissive license, they wouldn't have to do that. So we wanted to make it as easy as we could for anyone to contribute and for anyone to use SPAC. So we switched the license. That was a pretty extensive effort in the sense that we had to ask all of our contributors if they were okay with this change. And so we got approvals from around 300 people to do this. And I guess, that I view that as a sign that the community is pretty engaged, that they're willing to actually respond to our emails and say, yes, I'm okay with this license change. And some of them even had to track down their local legal organizations, and I felt a little sorry for them, but I was really happy that people came out for this and that we were able to get the relicense done. So the major new feature in the latest version of SPAC is called environments. You may be familiar with things like this from, say, Conda or pip. This is a set of packages that are grouped together and they get installed all at once. We've tried to combine sort of the virtual environment features of things like Conda and pip with some of the sort of manifest and lock file models that other language package managers are using. So if you used NPM or Cargo or some of these other languages, you can actually make a directory. You can put a single file in it that says what you want to install, and someone can sort of CD into that directory and type install and get all the things there installed. So this lets people actually version SPAC configuration with their projects. So if you're writing some code, you can put a spac.yaml file at the root level of your repo or in a subdirectory if you want to. You can write it sort of like this. You don't have to include configuration if you don't want to. This is sort of extra. And down here, you just list the things that you want to install. And these can have the same constraints on them that I showed earlier. But basically, the developers can put this file here. A user can check out the repo, and then you can CD in there, type SPAC install, and get everything set up the way that you need it for the project. And we spit out something that we're calling a lock file. It's a term that we stole from other package managers. That is essentially the full configuration of what this stuff concretized to. So it includes all the versions, all the compilers, everything that you would need to rebuild that thing if you wanted to build it somewhere else. This is sort of becoming a standard model. I think it's pretty cool. It basically gives people a file format for a set of installations, and they can hand that around and share it. So if you want to build something that you built on one platform on another platform, you can hand them this spec.yaml file. They can go and reconcretize it and install something that's sort of custom tailored for their platform. If you want to rebuild the exact same thing on the same platform, you can hand off the lock file and say, here's exactly what I built. If you want to debug it and find the same bugs, you can go and rebuild from the log file. The other cool thing that this enables is that we're trying to target containers as a deployment environment for Spack. We would like developers to be able to use Spack to build all the things in their containers. And so with this model, you can have sort of one Git repo, like this Docker demo repo. You can put a Docker file in there, and the Docker file might say something like this, where you say, I want to build from this image. I want my working directory to be /build. I'm going to copy in that spack.yaml and just run spack install. And so this really simplifies the workflow for building a bunch of packages in a container. The spack.yaml file, like I said, can just have a list of specs that you want to install. So you can have HDF5, OpenMPI, Fabric, SQL Fabric, or Nalu in there. And that makes it very easy. You don't have to write a bunch of commands up here to install everything and get Spack cloned. You can just use one of our base images from Docker Hub, and then you can run Spack install in your container. And so we're hoping this will help people build things like Singularity images, where you would just build this thing with Docker build and then run with Singularity or some other tool. And one of the things we're looking at sort of on the roadmap is making it so that Spack could automatically spit out recipes like this. There are some things that we could do to reduce the size of the containers because we know how the dependencies are laid out. So we could build a container that that excludes things like build dependencies, so that you would do a multi-stage build and make a smaller container with just the things that you need at runtime. Or you could have an option to build a dev container where the dev tools are included. It really depends on your use case. So on the roadmap are a number of things. One of the big ones is that we're trying to support the ECP with binary builds. And we are building something called Spack stacks that I think will help facilities to deploy things more easily. There's this chaining feature, I'll talk about that in a little bit, that lets you have one Spack instance depend on the packages installed in another. And we're working on architecture-specific binaries so that we can do optimized builds, make a binary package out of them, and know where they're reusable. So that if we optimize for, say, Skylake or AVX 512, we know that the binary that we produced is usable on machines that support that. And then finally, we're working on improvements to the concretizer. So under ECP, Spack started being used by groups to sort of integrate their related projects. We are trying to make it so that all the ECP software that I showed on that first slide could be deployed at the facilities in a uniform way, so that the different DOE facilities can actually share build recipes using Spack, and we would have reliable recipes that build at the DOE facilities. To do that, we need a lot of testing. And so one of the things that we're doing under ECP is we're actually working on a DOE-wide continuous integration project. And so this is another thing I'm involved in. And it's related to Spack in that this is what we really hope to use to test this whole ecosystem. So one of the problems you may have seen at HPC centers is that if you try to deploy a CI framework that's usable by users, most of the CI tools like Jenkins or even GetLab out of the box, they assume that the runners are going to run as some shared user. And at most of our HPC sites, at least in DOE, we have strict security requirements that say that the users can't share data and that they really need to run as their users on the machine. And that's important both for security and also for things like billing for hours, because your hours are associated with your Unix account on the machine. And when you say, SBatch, or when you submit a job, it knows what banks to charge based on what user you are. And so we wanted to be able to integrate with that. So what we're doing is we've contracted out to a vendor, Onyx Point, to modify GitLab so that it can run better in an HPC environment. And so there's two things we're building. One's a set UID runner and the other's a batch runner. And I'll talk about that a little bit. So the set UID runner, this is something that basically you would have a GitLab server. It would be deployed by your site, and your runners would be deployed across your machines at the particular site. And the runners, the runners are set up to run your jobs as whatever user triggered the job in GitLab. So if you do a pull request or if you push something to GitLab, GitLab knows that the users on the runners are the same as the ones in GitLab, and it tells the runner to run as whoever did the push. So that gets us the OS level security at the center, and then we're able to actually have runners that integrate with the batch system and that users can actually submit jobs from. and that are isolated from other runners. And so that lets us do CI jobs and to use GitLab CI, which is sort of similar to Travis, if you've seen that. It's configurable with a single YAML file, and it sort of democratizes the CI process because each of your users can just put a YAML file in their repo to enable CI, and they can automatically run on the HPC resources. The other thing that we're doing is the regular set UID runners would run on the login node. And so, yeah, you could run srun from within one of those, or you could run, you could submit something to the batch queue, but we'd really like to have it so that the CI system knows about the batch system. So we've built these batch runners as well in conjunction with Onyx Point. And so these are pretty much like set UID runners, except for instead of running the job on the login node, making the user submit the job and wait for it, these runners just submit the job to the batch system. And then GitLab sits there and waits, and the job starts running when the job in the batch system starts running, and it stops when it's done. And the cool thing about these is that you could have many jobs active at once in one of these runners at the same time. And so with all that, we think that we can set up a pretty nice CI system at the facilities, and that it'll be low maintenance because the facility just deploys the runners. You don't have to manage the security or manage CI systems per team. You can have one instance of GitLab trusted runners deployed across the facility and have them running jobs on behalf of users. So our final goal with this is to have all the DOE sites running these types of runners and hooked up to one GitLab instance. And there's a little bit of authentication federation that we have to do for the final stage here, but we're hoping to have this done by next month. Sort of our first prototype of this final unified GitLab instance. And so this would actually let you push to one place and have your jobs run as your user across all the DOE systems where you have accounts. And so we're hoping that will both enable testing things like SPAC, but also enable teams at DOE to make sure that their software runs in all the different environments that we support. Because the environments at Oak Ridge, Argonne, Livermore, Los Alamos, they're pretty different, and you need to test there to make sure that your code continues to run. So how does this all, so one last thing is that the vendor, Onyx Point, who's implementing this stuff, they have a relationship with GitLab. And so we're expecting that at least the set UID and the sort of authentication federation pieces of this can be upstreamed, and so that it would be in GitLab and it would be something that you could just use. The batch integration, we will obviously make sure that continues to be used within DOE, but we're not sure that GitLab will take it into the main line because it's so HPC specific. So we're working on that, but we're hoping that this stuff can be maintained for the long term and live beyond DCP. So what does all that have to do with SPAC? Essentially, we are trying to set up automatic builds of all these SPAC packages on machines that we care about on a regular basis. And so if you look at how SPAC is set up now, the users would submit pull requests to GitHub with their new packages or whatever. We test that in Travis, and right now we basically just run unit tests on SPAC itself. We would like to add mirroring capabilities so that if the source tarballs for packages go away, that we actually have a mirror for them. So we want to be able to have a mirror out in the cloud for all the different packages that are in SPAC. And then users could download from the mirror if, say, if SourceForge goes down and some of the tarballs are unavailable. The other thing that we would add there is we would add GitLab CI. So Travis isn't sufficient for this kind of testing because it basically lets you run on Linux x86 systems in a container. And so, and the builds are time limited. So you have a limit of 50 minutes for the different builds that take place. With GitLab, we can run on our own resources with all the stuff that I just showed. So we would have some cloud builds with GitLab, and we actually have this working right now where we have containers in the cloud building SPAC packages and storing binaries on a prototype binary mirror. And so this would basically make it so that if you say SPAC install something, you could download a binary for it and not even have to build it. And what we eventually would like to do with all the stuff we're setting up for DOE is add HPC systems into that mix so that at the HPC centers, we would also be doing builds on a continuous basis. They'd be optimized for the different platforms DOE cares about, and we'd have binaries available for them so that for most users, when you say SPAC install, you just download the binary package and have it in minutes instead of having to wait potentially hours for the build. So that's where we're going. Under ECP, They are trying to set up sort of a release process so that the code teams that are working on all these different software packages can work together on smaller releases. So maybe the math libraries team would work together on a release, the Viz guys would work together on a release, and the programming models team would work together on a release. And basically what this means is that they make sure that all their stuff links together and works properly. And then all of that gets integrated into an EPwide software release. And so there's the prototype version of this. You can find it on e4s.io. I guess it's not on this slide, but they've built a container with a lot of the different ECP products where basically it's a giant container that has everything installed with Spack with a module system in the container. I don't think that's actually how the facilities are going to deploy these things, but it's sort of a demo environment for what's it like to run on these machines and how might a facility deployment look. And it's a proof of concept for the fact that we can build all this in a single container. This is sort of more on the SDKs. That's these smaller per area releases that the ECP folks are doing. I guess the main point here is just that ECP is supporting this software release process so that we can have different teams working together. And the eventual goal is to make this stuff available through SPAC, through the stuff that I showed, but also to maybe push some of it out into other distros like OpenHPC, or have the facilities install things through, say, a larger SPAC distribution. The other thing that we're working on the roadmap is called SPAC stacks. This is something designed to simplify facility deployments. And so you can think of it as an extension of the environments work that I showed earlier. So environments basically allow a user to put a file in a directory and have a list of packages that they want to install. SPAC stacks take that and make it combinatorial. And so if you're a facility, you might list some definitions for things like what compilers do you want to build with, what MPIs do you want to build with, and which packages do you want to install with all of those different tool chains. And so what this does down here is you can say, okay, I have a set of specs. It's essentially the cross product of all of these lists up here. So basically every package in this list would be built with GCC and MBAPICH, GCC and MBAPICH 2.3, GCC and OpenMPI, Clang and MBAPICH, and so on. And so this is a much more concise description of that. And our goal is to make it so that the facilities can actually have a file like this that describes the inventory of packages that they have available. And when you install this, it would spit out a lock file just like the environments do already. And so you could see exactly what versions of things are installed at the facility, and you could potentially reproduce them somewhere else for debugging. That's important for us at Livermore because we actually run on 3 different networks. So we have our sort of open side stuff, a slightly more restricted network, and then we even have a classified network. And so we want to be able to reproduce these builds exactly across those different environments. So this is why we're doing this. The other thing that's associated with a stack is a particular module configuration. And so you can embed your module configuration in this file as well to show how the modules for your site look. And our goal with that, at least here at Livermore, is that we'd like to be able to have stacks active for both the traditional Livermore way that modules looked, but also, say, the Los Alamos modules, so that if we have users from their site that log in here and want to run on our machines, they can run in an environment that they're familiar with, and they might have their modules available to them as well. And we could have both side by side. They can pick which one they want. Eventually, I guess we'd like to consolidate that, but since we don't see any agreement in the near future, having both environments is kind of the next best thing. The other thing that we're working on is specific target information in specs. And so right now, if SPAC was designed as sort of a build from source system. And if you go and you install something, it will label the install as, say, x86-64 if you're on an Intel or an AMD machine. And what we don't do right now is label that as Haswell or Skylake or a specific model of CPU currently. And so it'll be optimized for x86-64 because you built it from source on, it'll be optimized for Skylake because you built it from source on a Skylake machine, but it'll still be labeled x86-64. And if we make a binary package out of it right now, knowing exactly where that can be used can be tricky. And so what we want to do is embed enough metadata in the binaries themselves so that we know what environment they were built for, and so that basically every SPAC build has either an march or an mCPU argument passed to the compiler each time it's run. And basically that would enable us to figure out that, oh, I'm on a Skylake, I'm installing a binary I want to grab the Skylake binary. Or if I don't have that available, I would grab the Haswell binary instead of, say, the generic unoptimized binary that's out there. This is something we're working on now. We're expecting that this will be done by this fall. So that's all for the roadmap. The community is growing pretty rapidly, as you can see from the map. SPAC is targeted at users, developers, and also HPC cluster installations. So it's sort of serving a wide variety of people, and we're trying to make it so that the same packages can be used by just people who want to install and run things, by developers, and by facilities who want to deploy lots of software. It's central to ECP's software strategy now. It's sort of the de facto software deployment tool. And we're working on building an ecosystem around that where it'll be much easier to install software on DOE HPC machines. And we have a lot of new things on the roadmap. So hopefully those are interesting to you all, and that they would help the Champions community as well. So go and grab SPAC. Just go to spack.io or visit us on GitHub here, github.com/spack/spack, and give us a star if you like it. And yeah, we hope to see you on there. We have a Slack site as well where you can communicate with us, and there's a mailing list. So feel free to join and ask questions, and hope to see you there. Thanks.
Thanks a lot, Todd. That was great. We did have some questions in the chat box, but some of the users were kind of helping one another out. So I think we just have maybe a couple of outstanding ones. When you were going through SPAC stacks, I was thinking the same thing as Alden was. Do you have an option to deal with elements of a matrix that don't work? Is it resilient for builds that fail? Is it an individual task type thing, or if you hit a particular roadblock, does it kill the rest of the builds in the matrix?
It'll be best effort. So essentially, if something fails in here, we'll try to build as much of the DAG as we can. Yes, we have. So there's a lot more conditional logic in the final version of this spec. This is sort of the prototype. You could put down here in your spec list that you have a matrix, but you want to exclude things that meet certain criteria. Or if you're on a machine with a particular architecture, maybe you only want to include things for that build on that machine, or maybe you want to exclude stuff that doesn't build there. So we have methods to express that. You can do it based on environment variables or based on aspects of the machine. Okay.
We have one. How far down the DAG does the SPAC go? For example, if I have Qt4 in user, will SPAC use it if applicable, or build its own if I install something that needs it?
So I can show, I guess, I'm only sharing PowerPoint right now, right?
Yes.
Let's see, how do I get out of here and I want to share my web browser. Can you see this?
I still see your PowerPoint.
Okay, how do I do this? Stop. If I say stop video, is that going to stop your whole recording?
No.
No, just
stop sharing.
Okay.
Yeah.
All right. Okay, so now let's try again. Start video. Oh, that's my video. No, where's the share screen option?
Let me see.
Down at the bottom, there's a
cancel. I'm not seeing that right now on my video. Maybe.
It should, maybe, do you see it at the top? Yeah.
Okay, good. Share, let's see. Okay, yeah. So we have this facility for external packages. Can people read this okay?
Yep.
If you go to spack.readthedocs.io, there is this build customization section, and it talks about external packages. There's a file that you can specify called packages.yaml, and you can put this stuff in like your environment file or in your stack file, where essentially you say, here's the packages that I have on my system. For OpenMPI, these are the paths where you can find it. And this is a spec, this part right here, where you give SPAC as much information as you can about what's installed on the system and what compiler it was built with and so on. And then you just say, this is where it's installed. So yeah, if you have Qt installed in your system somewhere and you want SPAC builds to take advantage of it, you can just add it here. The only caveat for that right now is that we don't let you specify really deep dependencies in here. So like we don't currently have a way for you to specify the whole DAG. Not that you would necessarily want to write out the whole DAG for Qt. But if there's something in there that you need a deeper dependency for, you may have to do a little more configuration.
Okay. There was another question up above, and this one kind of went back to, remember you and I were chatting about some of our friends at INL had done kind of an EasyBuild versus SPAC. They'd been using EasyBuild for a long time, and they were starting to explore SPAC. But one of the champions asked, should I be using EasyBuild or SPAC? And that's kind of a subjective question, but do you have any tips or pointers as to, if you're looking for the solution for your HPC center, how do you make that determination?
So, there's a lot of similar features. I would say the things that really differentiate the two are that in SPAC, you have a single recipe per package. So the amount of configuration that you have to write is potentially less than what you would have to do with EasyBuild. So you write one of these, or you use what's already available, and you don't have a million different easy config files on the system. And we do the dynamic dependency resolution for you. So you can very easily install something that's not in the standard set of things that EasyBuild provides, or that SPAC provides if you want to. So I don't know how much sense that makes, but that's sort of the main difference is that we actually do dependency resolution. We maintain a database of everything that's installed, whereas EasyBuild kind of just gets it installed and installs the modules, and then it's done. So for example, like you can't uninstall with EasyBuild. And I guess I don't know. I would say that plus the I'd say we're developing a lot more features on the near term roadmap, like for containers, like the SPAC stuff and the environment stuff that EasyBuild doesn't support. So I don't know. I think it's up to you all, which one you use, but that's the main difference is that I think for EasyBuild, you pretty much have to write a config file per version, per configuration that you want to install. So if you CD into like the HDF5 directory in the easy configs repo, there's like 110 different configurations for HDF5 in there. Whereas with SPAC, it's one file like this, and you basically specify what you want on the command line or in one of these YAML files.
Okay.
Does that help? I guess I can answer more specific questions about the differences between the tools if you want, but I guess I don't know what.
We can certainly, since you're a champion as well, somebody could certainly start a thread on the champions mailing list, and we could have that longer discussion, I guess, over the course of time.
Yeah. I think there's actually a presentation from the EasyBuild user meeting that was fairly recent by Massimiliano Colpo, who's one of our SPAC developers. He did a long presentation about SPAC. So if you're interested in the differences and in what the different points are that are different between the two tools, I think watching that would be pretty helpful. So I can send you a link to that.
Okay, that'd be great. We can put that out on the champions list. And so one of our colleagues, Davida at NREL, or I'm sorry, NCAR, asked if the part that Onyx Point has developed, the batch submit piece, will be shared even if GitLab does not merge it.
The batch, yeah, we'll share that. We'll make it open source and it'll be available on some DOE repo. I think it's actually out on GitLab.com right now. So like if you go to GitLab.com/Onyx Point Golang, yeah, this is the little library that they wrote in Go to adapt for different schedulers. So it supports Slurm, LSF, and Cobalt right now. And there is there's a batch runner. And so if GitLab doesn't accept that, we'll definitely put the batch runner online and have instructions for how to deploy it with GitLab, because we're definitely going to continue using this.
Okay, great. Karen Tomko asked if we were going to make these slides available. Will you be able to make those available for us to post on the champion side, or?
For sure.
Okay. There again, when we start dealing with DOE projects, there are always a few bottlenecks on occasion. So I wanted to make sure that was okay to have the slides.
Oh yeah, for sure.
Okay, great. Does anybody else have any questions for Todd? We're getting right to the top of the hour, and this has been outstanding. Todd, FYI, we had 78 attendees at one point.
That's awesome. Well, thanks to everyone for coming.
Somebody asked, when will you hear about PERC? I guess that's Marissa. You may be able to answer that better than anybody else.
I think some of the responses are going out. We're in the process of still kind of juggling those. But
okay.
Yeah, I know technical papers. The responses went out on those, and we have a few others that should be coming out any day soon.
Levi Baber at Iowa State is heading up that proposal, and so he said like 1 or 2 days, I think.
Cool.
And he's been responsible for committing a lot of R packages to SPAC. So I think we have him to thank for our really good R support.
Excellent.
Okay, great. Yeah, I'm kind of excited. I need to work my way back into the core team here at Arkansas and start building more packages. This kind of gives me renewed, rather than creating a solution to fix the misery of building packages, I kind of just step back from it. So this might actually make things manageable.
Cool. Yeah, definitely let us know.
Okay.
See you on Slack.
Yeah, definitely. I can catch up with you there for sure. Anybody else? Everybody's mentioning excellent presentation. So yeah, I would concur. This is probably the biggest crowd we've had, and probably the most questions we've had about a product. So it looks like this was well received for sure.
Well, yeah, thanks for having me. It's nice to talk to a new community. I did not realize that you guys had this mailing list, and some people told me that there was SPAC discussion on the champions list. So I thought I'd try to join.
That's great. We have one. Bennett, do you have a quick question? Stacking local space repositories with the community ones.
Oh, yeah. So I mentioned, okay. So there's two things I guess I'll talk about there briefly. One is that if you go to the docs here, there is a package repository section here. And there's a repos.yaml that you can set up, and basically you can say SPAC repo create. It'll make a directory for you where you can create your own packages, and they can be stacked on top of the built-in ones. So if you have your own private repo, it can have its own dependencies inside of it. You can actually override packages from the built-in SPAC distro, and you can depend on SPAC packages from the main SPAC distro too. So like you can have a package of your own that depends on OpenMPI and just uses the OpenMPI from SPAC, and so on.
So that receives some positive feedback there. And then I guess the last burning question that people wanted to know is, will you be at PERC?
Oh, yeah, I plan to attend if our tutorial is accepted. So like I was planning on going with one of our other developers and giving the tutorial along with Levi.
Okay.
So I hope so. Does that affect our submission? Is that who's on the call?
It doesn't hurt.
You're not coming? No.
One other FYI, Todd. One of our close, I think she's considered one of the developers, but she certainly works closely with them. Vanessa Sochat's as one of the champions as well, and she's worked a lot with the Singularity team. So she was kind of watching closely as far as the container integration and things like that goes. So there may be some side conversations there between you and Vanessa.
Yeah, that would be great. We've also talked to Greg Kurtzer and the folks at Scilabs about potential integrations as well. So we're pretty psyched about that.
Yep, Greg's great people.
Yep.
Awesome.
Okay, well, thank you so much. And I will be in touch on the side. And I guess when we get your slides, we'll go ahead and put those up. And we usually put those out, the link to the video as well as the link to the slides. So it's kind of there for posterity.
Okay, I guess, one more thing on the repos question. So this is repos for the package recipes themselves. And so we have that. And the other thing that we're adding is something called chains, where you could have the actual installations in one SPAC instance depend on installations from another, and so on. And so like the Fermilab folks have done, they've contributed that feature. And they've used that basically to allow a facility to have some packages installed, to have app teams install some packages that depend on those, and then to have developers sort of work off whatever the team's deployment looks like. And I think that should land pretty soon here, in develop at least. And so if you're interested in that, that's sort of another way to stack packages in SPAC. And that can reduce deployment times because you don't have to install the dependencies. They're already there.
Okay. That's cool too.
Yeah.
All right. Well, we're right at the top of the hour, and I certainly appreciate you taking time out of your day to do this, and welcome to the community. You just signed up here a couple of weeks ago, so I guess it's just your official greeting.
Yeah. All right. Thanks a lot. And thanks
Thanks.
for coming.
Thanks,
Thanks
everyone.
everybody.
Yep. Bye.
Bye.
Bye.